And welcome to this Any Excuse for a Chemistry Experiment. We are with rates of reaction. This is video number 2. Today we're going to be looking at two parts. We're going to be looking at collision theory, and then we're going to look at how we change the rates of chemical reactions. Start off with collision theory. Collision theory requires us to know the terms of both of those two words, collision and theory. Collision, this is when two things are going to hit each other and a reaction is going to take place. If no reaction takes place, no collision has happened. A theory, well, this is an idea that is backed up with scientific evidence. The reason it's called a theory and not fact is that the theory might change as new evidence arrives by new technology or scientists working on it in a different way. Collision theory states that particles must collide with enough energy for a reaction to take place. Let's have a look and see what that really means. Particles must collide with enough energy for a reaction to occur. So when we look at this at a particle level, we call it the particle model. What we're doing is we're looking at particles and that they must be moving or vibrating. Now particles must be colliding. So if I have this particle moving in that direction, and this particle moving in this direction, when they collide in the middle, a reaction is going to take place. And a new product is formed. However, what happens if the particles don't collide with enough energy for a reaction to occur? Well, they're going to ricochet off each other and we don't have a successful collision. Something like this. The particles could be moving with the right amount of energy, they might just ricochet off each other, so they will just change their angle there, look. No reaction occurs. Or they might be moving so slowly that what ends up happening is they bump into each other with the correct orientation, but instead of colliding, they bounce back on each other. So there we have it. Particles must have the right amount of energy and the right orientation for a reaction to occur. If they have the right amount of energy but the orientation is wrong, they're going to ricochet off each other. If they have the right orientation but not the right amount of energy, then they'll just bounce off each other as well. A collision must result in a reaction. So now we're going to look at the second part. How do we change the rate of those chemical reactions? Well, there are 4 ways that we can manipulate a reaction. Number 1 is temperature. We can increase the temperature in order to make the reaction happen faster, or we can decrease the temperature to make the reaction slower. We could change the concentration. If we have solutions, then the number of particles in those solutions makes difference. More particles will equal a faster reaction, less particles or a lower concentration will mean a slower rate of reaction. This is also true for pressure in gases. Concentration and pressure are going to be the same answer in your exam, so you can only use one or the other. The third one is going to be surface area. If one of your reactants is a solid, what we can do is we can grind it up into a powder, increasing its surface area, and then that would make the reaction happen faster. Lastly, is a catalyst. We can add a catalyst. Now you might have come across catalysts in your biology. Enzymes are a form of biological catalyst, but there are also chemical catalysts, and these are going to make some reactions happen faster. Temperature. Changing the rate of a chemical reaction, in other words, the number of successful collisions that are taking place, can be changed with temperature. If we have a look at our particle again, our particle is going to be vibrating, isn't it? If I add some heat to that, what ends up happening is the vibration gets bigger. The particles are going to be moving significantly more. meaning more particles are going to have enough energy for that reaction to take place. Let's have a look at concentration and pressure. The same scientific principle, one is going to be in solution, that's concentration, and the other one is going to be in a gas state, pressure. I want you to imagine that we're talking about the numbers of particles in a fixed area. If we have a fixed volume and the number of particles are there, then we have a concentration. If we want to change that concentration, then what we're going to need to do is put more particles into the same fixed area. Now, for a collision to take place, what we're going to need to have is we need to have another particle that is there to react. If I increase those numbers of particles, then I've got a greater chance of a successful collision between two of my particles. Now, this doesn't happen consistently. What ends up happening is as the concentration increases, then there's going to be competition for collisions between those particles. So if we have the similar situation to here, we have those particles there, then we have the same concentration and we have the same rate of reaction. If I now start to increase that concentration here, I will definitely increase my chances of collisions. But what's also now going to happen is some of my new particles are going to be colliding with each other. So the increase in the rate of chemical reaction begins to slow because too many particles are getting in the way to slow those reactions down. You'll see this potentially in your required practical. So surface area. What I'd like you to consider is if this solid was put into a reaction, then only the particles on the outside of our substance here could react. The particles on the inside of our cube couldn't. So it's only the surface area that is able to react. So let's have a look and see what our surface area would be in total. Imagine this was 2 centimetres by 2 centimetres. So the surface area of one of the sides is 2 times 2 is equal to 4 centimetres squared. But I've got 6 sides on a cube, so I need to do 4 times 6 is equal to 24 centimetres squared. Now what I'd want you to imagine is we take our cube and we cut it into 8 equal sized cubes. There we go. So we now have 8 equal sized cubes. Now each of those is going to be 1 centimetre by 1 centimetre. So let's do the maths again. 1 times 1 is equal to 1 centimetre squared. So the surface area of one of them sides is 1. But remember, we've got 6 sides on a cube, so that equals 6 centimetres squared. But I've also got 1, 2, 3, 4, 5, 6, 7, 8 cubes all in my thing. So I need to multiply that up by 8, which is going to give me a grand total of 48 centimetres squared. So long as we have the same volume, the same mass of our substance, and all we're changing is the surface area of it, then we will increase the rate of reaction because we have a greater surface, we have more particles that are available to react. Remember that, the same volume, the same mass, but smaller particles means a greater surface area. So there's a couple of bits of recall that we need to remember here. Catalysts tend to be those transition metals. Do you remember from year 9 when we looked at the transition metals? One of their properties is that they are good at catalysts. The other thing that we need to remember back to is our bond energy calculations and our bond energy sketch graphs. We start off with the reactants. Remember, we break the bonds and that requires energy. So remember, we add energy. Energy is released when new bonds form. So we go down to the minus side. And then the amount of energy that is left in the bonds of the product would be lower. This is a classic profile for those exothermic reactions. But what happens if we have a catalyst? If we add a catalyst, then it reduces the amount of energy that is required for that reaction. So our energy spike here, the amount of energy required for the reaction to take place is significantly lower. Do you remember it's called the activation energy? This one that requires significantly more energy is the activation energy without a catalyst. Now there are two things that we need to know about a catalyst. Number one, it reduces the energy required for a reaction to take place. And number two, it provides an alternative pathway for the reaction. We don't need to go into a lot of detail about this. We tend to go into it at A levels, but what we need to do is we need to remember that it reduces the energy required for a reaction to take place, and it provides an alternative pathway for the reaction, meaning that we have to add in less energy so our reaction can take place much more efficiently. So there we have it, looking at changing the rate of a chemical reaction. Now's a really good time maybe to look at your revision guide. There's some questions that you might want to work through to assess your understanding. Make some notes and test your knowledge as you go. I hope you found this video useful. Check out video number 3, that should be coming in the next couple of days, when we will look at reversible reactions and Le Chatelier's principle. Thank you very much and keep safe. Goodbye.